Good morning, everyone. It is truly an immense honor to be here at the very first International Conference on Leadership in AI, which is a significant part of the prestigious ICONS series. This conference is not just any event. It stands out as a remarkable gathering in the world of AI. The ICONS series has always been known for its high-profile nature, but this particular conference takes it a step further. It offers a unique opportunity that we don't come across often. Here we have the creme de la creme of the AI world coming together. We're talking about experts who have spent decades in the field, conducting in-depth research. There are also researchers who are at the forefront of new discoveries, constantly pushing the boundaries of what's possible. And let's not forget the innovators, those creative minds who are coming up with brand new ideas and solutions. They all hail from all corners of the globe, bringing with them a diverse range of perspectives and experiences. For a long time, I've been looking forward to this event. It's a one-of-a-kind platform where we can share and exchange ideas in the dynamic field of AI. This field is like a living, breathing entity, constantly evolving. New breakthroughs are happening almost every day, whether it's in machine learning algorithms, natural language processing, or computer vision. My name is Gabriel Silva-Atencio, and today I'm extremely excited to present my in-depth research on cognitive incident and problem management, or CIPM. In the rapidly evolving landscape of computational science, we're witnessing a massive and revolutionary shift toward autonomous systems. This shift didn't happen overnight. If we look back at the history of computing, it's like taking a journey through time. In the early days, we had simple calculators that could only perform basic arithmetic operations. Then came the mainframe computers, which were huge, room-sized machines. They were powerful for their time, but they were also limited in their capabilities. As technology advanced, we moved into the era of personal computers, which made computing more accessible to the general public. And now, we're in the current era of super powerful, interconnected systems. These systems can process vast amounts of data in real time, and they're used in everything from smartphones to large-scale data centers. However, when we look closely at the realm of IT operations, true autonomy remains an incredibly elusive goal. Most current systems are merely reactive. They're like firefighters who only show up after the fire has already started. These systems lack the cognitive depth required to manage modern, complex environments. Modern IT environments are like a vast and intricate web. Picture a large-scale data center. It's not just a room full of servers and equipment. It's a complex ecosystem with thousands of interconnected components. There are servers that store and process data, storage devices that hold vast amounts of information, networking equipment that allows different parts of the system to communicate, and countless software applications that perform various functions. Each component is like a unique piece of a puzzle, and current systems just can't handle this complexity effectively. To put it in perspective, think about a large-scale data center. It's like a city. There are different neighborhoods, each with its own set of rules and functions. The servers are like the buildings, the storage devices are like the warehouses, and the networking equipment is like the roads that connect everything. And just like in a city, if one part of the system fails, it can have a ripple effect on the entire operation. My work proposes a generative AI framework that's specifically designed for trustworthy autonomous IT operations. It's not just about creating any framework, it's about creating one that can be trusted. We aren't just looking at how to fix things faster. That's a common goal, but our approach goes much deeper. In today's digital age, security and verification are of utmost importance. Just imagine the chaos that could ensue if an IT system were to be compromised due to lack of proper security measures. For example, in a financial institution, a data breach could lead to the loss of sensitive customer information. This could include things like credit card numbers, social security numbers, and bank account details. And the financial losses could be in the millions of dollars. Over the next 20 minutes or so, I'll take you on a detailed journey. First, I'll walk you through in great detail why current methods are failing. It's not just a simple matter of inefficiency. There are fundamental flaws in the design and implementation of these methods. For example, the way data is collected and analyzed in some current systems might be outdated. Some systems rely on old-fashioned data collection techniques that can't keep up with the volume and velocity of modern data. In the past, data was collected at a slow pace and it was mostly structured. But now, we have a flood of unstructured data coming from sources like social media, sensors, and mobile devices. And current systems often struggle to make sense of this data. Then, I'll explain how we can harness the power of large language models safely. Large language models are a double-edged sword. They have great potential, but we need to use them carefully. We'll look at the different techniques and strategies that can be employed to ensure their safe use. For instance, fine-tuning is a technique where we take a pre-trained large language model and adjust it to perform a specific task. This allows us to make the model more accurate and relevant for our particular use case. Prompt engineering is another important strategy. It involves crafting the right prompts to get the desired output from the model. By carefully designing the prompts, we can control what the model generates and ensure that it's useful and reliable. Finally, I'll present the rigorous testing results that prove this framework's effectiveness. These results are not just numbers on a page. They represent real-world applications and improvements. Let us begin by closely examining the core problem we are facing today. We'll start by looking at the current state of IT operations and how it has evolved over the years. We'll see how the industry has grown from its humble beginnings to the complex and sophisticated systems we have today. We'll also touch on some of the key milestones in the development of IT operations, such as the introduction of cloud computing. Cloud computing has revolutionized the way we store and access data. It allows us to use computing resources on demand without having to invest in expensive hardware. And the rise of big data analytics has also been a game changer. It has enabled us to extract valuable insights from large amounts of data, which can be used to make better decisions and improve business processes. To understand the need for CIPM, we must first look at the limitations of current AI ops. Modern IT platforms have become incredibly complex, moving away from monolithic architectures toward highly distributed microservices and containerized environments. Traditional rule-based systems, which rely on if-then logic, simply cannot keep up with the sheer volume of telemetry data and the nonlinear way these systems fail. Currently, the state-of-the-art in AI ops relies heavily on discriminative models. These models are excellent at anomaly detection and correlation. Essentially, they are good at telling you that something is wrong or that event A and event B happened at the same time. However, this is the core of the problem. These models detect symptoms, not root causes. They lack the generative synthesis needed for actual self-repair. They can identify a fire, but they cannot describe why the fire started or prescribe the exact steps to put it out without human intervention. This gap between detection and prescription is what we aim to bridge with a cognitive approach. This brings us to the opportunity presented by generative AI and large language models. Unlike discriminative models, LLMs possess a unique ability to generate human-readable explanations and, more importantly, create corrective actions like scripts or configuration changes. We have already seen success in adjacent fields, such as automated program repair, which suggests that LLMs could potentially enable true self-healing IT. However, we cannot ignore the elephant in the room: the risk of hallucinations. In a production IT environment, an AI that generates a plausible-sounding but incorrect or dangerous command is a massive safety risk. Imagine an AI accidentally deleting a production database because it hallucinated a cleanup command. Unconstrained generative AI is simply too dangerous for mission-critical infrastructure. Therefore, the central challenge of my research is: how can we harness the generative power of these models while providing a 100% guarantee of safety and operational integrity? We need a framework that provides the benefits of generative synthesis without the risks of unverified execution. Our research is driven by a singular fundamental question: how can a system be designed to perform logical, secure, and verifiable autonomous IT operations using generative AI? To answer this, we developed the CIPM framework. CPM is not just a wrapper around an LLM. It is a multi-layered framework that combines generative AI with structured reasoning and deterministic safety constraints. It represents a paradigm shift from simple alert correlation to cognitive incident management. In this model, the AI doesn't just look for patterns. It attempts to reason through the incident, understanding the dependencies and the underlying logic of the system it is managing. By building a framework that enforces safety at every step, we move from a black box model to a transparent, verifiable process. We wanted to move beyond just guessing the fix to proving the fix before it is ever applied to the live environment. This methodology ensures that every action taken by the autonomous agent is grounded in reality and system policy. To evaluate this framework, we adopted a design science research approach. We didn't just test this on static data. We built a high-fidelity digital twin of a complex microservices application using Docker and Kubernetes. This digital twin allowed us to conduct safe, repeatable, and controlled experiments that mirror real-world production environments. For the testing phase, we used Chaos Mesh to inject 520 diverse incident scenarios. We didn't make it easy. The faults included infrastructure failures, application errors, latency degradation, dependency failures, and even gray failures, which are notoriously difficult to detect. We measured our success across 4 key dimensions: diagnostic accuracy, how effective the remediation was, the safety of the proposed actions, and the overall system performance. This rigorous testing environment ensured that the results we observed were not just artifacts of a simple setup, but were robust enough to handle the chaotic nature of modern IT operations. We wanted to see if the AI could truly handle the messiness of real-world distributed systems. Let's look at the first key result: diagnostic accuracy. When it comes to identifying the actual root cause of an incident, CIPM significantly outperformed the baselines. While traditional rule-based systems managed only 58% accuracy and discriminative AI baselines reached 72%, the CIPM framework achieved a remarkable 89% diagnostic accuracy. The 95% confidence interval for this result is between 86.4% and 91.6%, showing very high consistency. More importantly, we achieved a statistical significance of p less than 0.001 compared to both baselines. We also used QFactival to measure factual consistency. CIPM scored 0.81 compared to the baseline 0.65. This is a critical distinction because it proves that CIPM isn't just getting lucky or correlating symptoms. It is moving toward a true causal understanding of why a system is failing. It understands the why behind the what, which is the first step toward reliable autonomous repair. By achieving nearly 90% accuracy in such a complex environment, we demonstrate that cognitive reasoning is superior to simple pattern matching and root cause analysis. Beyond just diagnosing the problem, we looked at how effectively and quickly the system could fix it. The results here were equally impressive. CIPM-generated scripts successfully resolved 94% of the diagnosed issues, with automated tests confirming that the fixes worked in 88% of cases. To put this in perspective, standard pre-written runbooks were only applicable 60% of the time, proving that the generative approach is much better at handling unique or unexpected scenarios. The impact on speed was dramatic. The mean time to resolution, or MTTR, for the discriminative baseline, which still required human intervention for the actual fix, was 12.3 minutes. CIPM's automated resolution took only 4.7 minutes. This represents a 62% reduction in resolution time. For any business, a 60% faster recovery from downtime translates directly into significant cost savings and improved service reliability. By automating the synthesis of the repair script, we remove the human bottleneck that usually accounts for the majority of downtime in current IT operations workflows. Perhaps the most important part of this research is key result number 3, the safety validation gate. During our testing, we found that 6% of AI-generated corrections actually contained errors, such as dangerous commands, overly broad instructions, or policy violations. This is the hallucination risk I mentioned earlier. However, our deterministic validation gate stopped 100% of these erroneous actions. As a result, 0 unsafe actions were ever executed in our simulated environment. We also tested for adversarial robustness. While the system was highly resistant to direct prompt injection attacks, we did identify a vulnerability in knowledge-based poisoning, where an attacker could influence the AI's suggestions with a 15% success rate. However, even in these cases, the validation gate prevented any dangerous actions from being executed. The conclusion here is profound. Trust in AI for critical infrastructure is not earned by having a perfect AI that never makes a mistake. Instead, trust is earned through perfect error control. By assuming the AI might fail and building a deterministic safety net, we create a system that is safe to use in production. Moving into the discussion, CIPM introduces a new paradigm in IT operations. We are moving from a reactive, symptom-focused world to a proactive, cause-focused world with built-in safety. One interesting finding was the nature of human-AI collaboration. Audit logs generated by CIPM were rated as clear and useful in 87% of cases, with a high FLICE kappa of 0.74, indicating strong agreement among human auditors. This shows that CIPM acts as a collaborative co-pilot, augmenting human expertise rather than trying to replace it entirely. Of course, there are trade-offs. The end-to-end latency for a full diagnosis and repair cycle was 38 seconds at the 95th percentile. We call this the cost of thinking. While 38 seconds is much slower than a simple rule-based trigger, it is significantly faster than a human. This suggests a hybrid model for the future. Use traditional, fast automation for routine, simple issues, and use the CIPM framework for the complex cognitive events that require deeper reasoning and causal understanding. This balanced approach maximizes both speed and safety. We must also be transparent about the challenges in future work. Knowledge-based poisoning remains a real threat with a 15% success rate in our tests, which will require advanced version control and integrity checks for any documentation the AI uses for learning. There is also a computational cost. CIPM requires about 2.5 times more compute than discriminative models. Furthermore, we noticed that retrieval time increases as the knowledge base grows, from 320 milliseconds for 10,000 documents to 580 milliseconds for 100,000 documents. Looking forward, our next steps involve long-term case studies in real-world production systems to see how the framework performs over months rather than hours. We are also looking into integrating formal verification methods to provide mathematical safety guarantees for the generated scripts. Finally, we want to enhance the causal reasoning engine by developing tools for dynamic real-time causal graph inference, which would allow the AI to understand system changes as they happen, further increasing its diagnostic accuracy and remediation effectiveness in even more fluid environments. In conclusion, the Cognitive Incident and Problem Management Framework provides the first proven and tested blueprint for integrating generative AI into self-executing IT operations with built-in safety. We have demonstrated a significant conceptual shift, moving the field from mere alert correlation to true cognitive incident management. The key takeaway from this research is that trust in autonomous systems is not achieved through perfect performance alone. Rather, it is achieved through perfect error control, transparent reasoning, and clear escalation paths. When we build AI with the right safety constraints and deterministic gates, generative AI can indeed be a reliable, powerful foundation for the next generation of autonomous computing. By bridging the gap between the creative potential of LLMs and the rigid safety requirements of production IT, we open the door to a future where systems can truly care for themselves, allowing human engineers to focus on higher-level innovation. Thank you for your time, and I look forward to your questions.